Okay, so today we're talking about related rates. What are related rates? When you find the derivative of something, you're finding the rate at which something changes with respect to another thing changing. This can be modeled by dy over dx, which means the derivative of y changes with respect to the derivative of x changing. Here's an example of how this works. Say you have a circle that gets bigger as time goes on. This means that the radius and the area get bigger as well. If you want to find how the area and radius increase, you'll first need to know the area formula. Now, since both things change with respect to time, you need to derive both of them with respect to time. You'll notice that the derivative of t was never in the original formula, but we bring it in now because it changes the values of the derivative of a and the derivative of r as it changes. So now we must take the derivative of the area equation. On the left side, we get the derivative of the area with respect to time, which is otherwise known as the rate that the area changes as time passes. Now the right side is different. When we take the derivative of this side, we get 2 pi r dr dt. This is a very important step. Here's how we get this answer. Pi is just a number, so that remains constant throughout the derivation. Next we have r squared. The derivative of r is 2r, but we also need to add in the dr dt because that is how the radius changes with respect to time changing. So now the whole equation is dA over dt equals 2 pi r dr over dt, which means the rate that the area of the circle is changing at some point in time is equal to 2 times pi times the radius at that moment times the rate the radius is changing at that moment. Now at this point we have three unknowns, dA over dt, r, and dr dt. We need to know two of these things in order to find the third, so a typical problem may say that a circle is increasing in radius at a rate of 3 inches per minute and ask you to find the rate that the area is changing when the radius is 6 inches. So now you just plug in the values and solve, and you get 36 pi inches squared per minute. Sometimes people make mistakes by plugging the given values into the equation before it has been derived. This gives you incorrect values and others that you don't even need. People do this because they forget that the variable is not a constant. Other times people make mistakes in the derivation of the equation, forgetting that you must add the dr dt due to implicit differentiation. This also obviously yields wrong answers. Let's do another problem. Ship A is traveling due west towards Lighthouse Rock at a speed of 15 kilometers per hour. Ship B is traveling due north away from Lighthouse Rock at a speed of 10 kilometers an hour. Let x be the distance between Ship A and Lighthouse Rock at the time t, and let y be the distance between Ship B and Lighthouse Rock at time t. Okay, so part A asks for the distance between ships A and B when x equals 4 and y equals 3. This is a simple Pythagorean theorem problem, and we get that the distance is 5 kilometers. Now part B asks that we find the rate of change in kilometers per hour of the distance between the two ships when x equals 4 and y equals 3. So our objective is to find the rate of change of h with respect to time. After we establish this, we use our Pythagorean equation to find the derivative. We end up with 2x dx dt plus 2y dy dt equals 2h dh dt. Remember to put the extra variables in respect to time. This implicit differentiation step makes sure that all of the variables can be solved with the respect to time. Now it seems like we have a lot of variables, but we know most of them. X and y are given as 4 and 3. We also know that h is 5 because of our work in part A and the Pythagorean theorem. Now dx dt and dy dt may seem like scary variables, but we have them as well. They were given to us in the beginning when we were told that ship A was sailing at 15 kilometers an hour and ship B was sailing at 10 kilometers an hour. Now remember that we're going to put the 15 kilometers an hour into the equation as a negative value because if it were on a coordinate plane traveling west, it would be going in a negative direction. From here, you just substitute and solve and get that the rate of change between the two ships is negative 6 kilometers an hour. Now part C asks you to find the rate of change of this angle theta in radians per hour when x equals 4 and y equals 3. This is slightly different than part B, but it has the same general steps. Since we are finding an angle, we are going to use the trigonometric equation, which would be tangent in this case. Now, when we take the derivative, we must remember trig identities and use the quotient rule. Make sure you put in the variables with respect to time. After all of this, here's your equation. Now we fill things in. Remember that since secant of theta is h over x, so when x equals 4 and y equals 3, secant of theta is 5 over 4. From here, plug in the variables and solve. We get an answer of 17 over 5 radians per hour. This has been related rates. The most important thing to remember is to make sure that your variables are able to change with respect to something else.